Hello guys, I hope you're doing well. I hope your non-mock mocks are going suitably okay, and I hope you didn't get a soaking getting home from school like someone did on the A23. Please say hello in the comments, and I will warmly welcome you. So today's job is abstraction, decomposition, and algorithmic thinking. Before we get there, though, let's have a look back at some of the questions we've looked at before, some of the quiz questions, and see if you can remember the answers to these. Do say hello in the comments. Aditya, bonsoir. How are you? I hope all is well. It was the French exam today, wasn't it? I could see some concerned looking faces. It was French and food, so it was F day today. So quiz time, rewind. Let's see how many of these you can remember. Hi Chris, I hope you're doing well. Thanks for coming along. So this was one from, we got, d'accord, très bien. Alors, we've got, which law states that information, who else we got here? You can read it. Stick the answers in the comments. Hi Bogdan, how you doing? Thanks for coming along. Hi Swiftblade, hope you are well. Hi Hash Brown, I hope all is well with you. Hi Sergen, how you doing? And we've got some answers, and we've got hi from Flynn. Hi Flynn, thanks for coming along, brilliant. So we've got Aditya who has said B. We've got Swiftblade who has said B. Which law states that information has been lawfully and transparently? Flynn's come in with a B. Bogdan's come in with a B. This is all sounding rather good to me. And Sergen's come in with a B as well. So let's see what the answer actually is, shall we? And it is a B. We are all superstars. Nice and easy. That's something they like to ask, is that they often do a little sort of grid around these questions to make you guess what the different, and Hash Brown said B as well, good job, what the different laws relate to. All right, I think we've got a couple more of these. Which legislation governs the act of intellectual property theft? And it's that phrase, intellectual property, that I'm wondering if you remember, because what's that about, intellectual property? We've got Aditya who says B. Any more takers? Flynn who says B. It is looking quite good. I can see coming up, we've got Chris who said B. And so you guys are absolutely spot on, because it certainly is B. So that is outstanding. So it looks like you're pretty good on your laws. Bogdan with B. So that is outstanding. You are good with your laws. Right, let's go on to the next one then, because that was a bit too easy for you. I wanted to remind you actually that I did some videos over half term on oh hello, this is looking quite concerning. That shouldn't have been there. This is the one that I want you to do. So this is the nasty one. I meant to say to you, I've done 3 videos on my YouTube channel for system architecture. The first one is pretty straightforward. I know that Aditya saw it and said it's quite a straightforward video, and yes it was. It sort of sets the scene, the first one. And really the first one is just telling you that don't forget CPUs only use data and instructions, because they're both binary numbers. But the remaining 2 are going through the address registers, that which you've got in front of you here, and how the data moves around the CPU. So that could be useful for you. All right, so we've got Aditya who said A is the MAR, stores the address location of a data will be read. That is spot on. We've got Aditya who says B is the MDR. And of course the A in answer, or question A rather, the address register. We've only got 2 address registers. We've got the MAR and we've got the PC. Oh, it looks like Aditya's on fire here. I hope not literally. C, he says, is the PC, and it is the program counter is the next instruction to be run. Aditya has come in with D being the ACC, which stores those. Bogdan's come in with the entire thing. He said A, MAR, correct. B, MDR, correct. C, program counter. This is all ding, ding, dinging. Where's my ding? There it is. And D, what did you get for that, Bogdan? You didn't put the D in. Oh, DACC, you got it there. Guys, that's absolutely spot on. So have a look at that video that I've made. You're absolutely spot on. And I think this is the hardest thing. We've got, let's have a check. Sergen, yeah, you were spot on with MAR. Absolutely spot on. So the memory address register, the memory data register, and then the program counter. The program counter is simply kind of pointing at the next instruction. It's like queuing up where the next instruction will be held, the address of the next instruction. And then we've got Sergen said CPC, correct, that is the program counter. So listen guys, this is outstanding. I mean, we've tried to get this question right because it's hard to remember, isn't it? When you think about it, you've only got 2 address registers, the program counter, which is pointing to the next one, and then the MAR, the memory address register, which is the one that's currently being used as part of the fetch, decode, execute cycle. And don't forget, what makes the von Neumann architecture different is that instructions and data are held in the same memory, because they are logically similar in that they're both sets of binary numbers. All right, good. Enough on that. That is super impressive. So I think maybe I don't need to ask anything about that again. So what's this all about? Well, today we're starting paper 2 today. So this is Principles of Computational Thinking, Abstraction, Decomposition and Algorithmic Thinking. Now, I think this is probably the easiest part of it, and how they've made one entire sort of unit from this, or one topic from this, I kind of get. But this usually tends to be a fairly low scoring questions that they ask. 1, 2, 3 mark questions for this, but they will try and find out that you know what abstraction and decomposition is, and then what algorithmic thinking is for. All right, so that's the kind of plan today. And in the specification, it says that you need to understand these principles and how they are used to define and refine problems. All right, so this should be quite straightforward today. 10 minutes each. I reckon it'll be more like 7. There's my guess. So computational thinking, this is 2.1.1 in the specification. Right, so computational thinking. The idea behind this is that you take a complex problem and you actually take the time to understand the problems and look at to understand the problem and then think about a range of solutions that you could use. And the principles of computational thinking are abstraction, decomposition, and algorithmic thinking. So computational thinking is about solving problems and ultimately turning them into computer programs, which is where the algorithmic thinking comes into it. And then abstraction and decomposition are the 2 processes that you would do to get you towards algorithmic thinking. All right, so that's the intro there. And I mean, you've done this in year 9 to death. Now, abstraction. During the process of abstraction, you need to identify only the necessary information required for a solution. Ignoring information that's not required. Oh, something very odd has happened to my spelling of that word. Ogumpromug, which is an unusual word. That should be ignoring. That's an extraordinary spelling of ignoring. I don't know what happened there. So ignoring unnecessary details. We have the abstractometer there, which is deeply concerning on many levels. But I think one of the best sort of examples of this is the London Tube map, the London Underground map, because that is a really good example of abstraction. And the abstraction that's been used there makes it really easy to use, because obviously unnecessary details like roads and buildings and woods have been taken away because they don't need to be there. The River Thames remains in there as the only geographical feature, because it's quite handy to know whether you're north or south of the river when you actually get out of the tube, because that's a good way of finding your way around London. Also, the distances between the tube stops have all been made to be the same, whereas in reality, as you get closer to the centre of town, where you've got Oxford Street and Regent Street, the tube stops are only maybe a couple of 100 yards apart, whereas when you go out to the sort of outer bounds around Walthamstow, it can be 6, 7, 8 miles between tube stops. So it's all been made to look like it's the same distance apart, because you don't need to know that information because you're on a tube train. It will take you there. So that's the idea of abstraction. And they will very often try to get you to distinguish abstraction from decomposition, right? So that's that's really quite an easy one. Let's look at decomposition next. So we've got the example here of making dinner. And the notion of decomposition is taking a problem and breaking it down into smaller parts. And if you think about, if you think about FIFA, or you think about any game that you play, or you think about Minecraft, or you think about Windows, or you think about Mac OS X, or you think about Linux, there are lots and lots of different parts to this complex software. But you could actually break it down to just a sort of series of subunits. So the idea of decomposition is that you keep breaking a problem down until the part becomes so small that it can be solved really easily. And actually, when you've got a group of people working on a piece of software, it's beneficial to use this method because you're going to give. I mean, I'll use FIFA as the example. You might give one team the idea of updating the football kits to this year's colours. You might give someone else the job of the crowd in one stadium. You might give someone else one stadium, and so on. So you can break it down and down and down until you've got one person who's involved in the clothing of the crowd. And I only say that because on FIFA 2000 and where are we, 22, you can see that some people in the crowd have got ripped jeans, so they've gone into a ridiculous level of detail there. But someone had to make that, and if you break it down into its smallest element, it makes it easier to solve. Okay, and in this example with making dinner, you've got make starter, make main course, and make dessert. But each of those can be broken down again. If you look at the main course, you've got to make the meat course or make the vegetable course. And then in the vegetable course, you've got two more things to make. And of course, making mashed potatoes, you could break that down again to peeling potatoes, washing potatoes, chopping potatoes, putting potatoes. I'm not going to teach you how to cook potatoes, but you get the message, okay? This is what decomposition is, but I'm sure you're all pretty happy with that. So that's abstraction and that's decomposition dealt with. The last part of this, and I do think this is the easiest bit of paper too, is algorithmic thinking. I shall move slightly out of the way so you can see this. There you go, you can have half my head. So an algorithm is best described as a sequence of clear instructions. Now I know that you all know what an algorithm is, but in case they ask for a definition at GCSE, that's a pretty good one, okay? It's a sequence of clear instructions that are used to solve a problem step by step. So that is as good a definition of algorithmic thinking, or what an algorithm is, sorry, as you might need. Let's look at the idea of what a concise algorithm should be, a definition of a good algorithm, all right, the characteristics of a good algorithm. An algorithm is useful if it is unambiguous, if it takes you from A to B to C to D without any confusion, if it's complete, if it's accurate, if it's consistent, and if it's efficient. Now, oddly enough, questions around algorithmic thinking are ones that higher tier students often mess up because they know this. And it's very easy to skip over it and think, I know what an algorithm must be. I've written them in Python. Don't talk to me about algorithms. But don't forget, you do need to be able to describe the characteristics of a good algorithm. And that's the 5 words I've got there. But also to define what an algorithm is. So I know it's obvious, but just take a minute or two to make sure that you'll be able to reproduce that in the exam, okay? Because it's often the case that higher tier students chuck away some of these easy 1 or 2 marks, and you do that sort of 4 or 5 times in a paper, and suddenly you're a grade boundary and a half away from where you should be. All right. So that is the algorithmic thinking part. So thinking computationally, a lot on the screen here. Now, just to be clear, and I'm using a bit of Python here, computational thinking is not the same as programming. It's just not the same. Programming involves instructing a computer what to do and how to do it. That's the definition of programming. Computational thinking, on the other hand, enables you to work out exactly what to tell the computer to do. So if you think about pseudocode, the process of creating pseudocode is thinking about how a computer needs to be instructed how to perform something, okay? So looking at the example of brushing your teeth, you will need a toothpaste and a toothbrush. You will need to sink in the water. You will need a sink with water. Yes, correct. You'll need to put the toothpaste on the toothbrush and so on. Although it's a really simple activity, it involves many steps. And if you miss one of these steps out, the whole thing won't work. If you try making a cup of coffee without a cup, well, A, you won't have any coffee, and B, you'll end up in A&E in the Burns unit. So, it's if you try making a cup of tea, but you forget to stop pouring water out of the kettle once your cup's full, you're going to irritate all sorts of people. So I know it's stating the obvious, but that is the notion of computational thinking, all right? it enables you to work out exactly what to tell the computer to do. So it's one step further removed from programming. Programming is writing the code itself. I hope that makes sense. So that's the thinking computationally part. What I thought might be useful at this time as we jump into quiz time, because that's really all there is for this. This is quite a straightforward one. 15 minutes to go. I might even finish early. But I do have a few questions for you. This one. This is an example of a past paper question, and it appears exactly like this. So this is a 4-mark question, 1, 2, 3, 4, and they've given you a list of the definitions. So what do we think it is in order of the numbers? What do we think, guys? What do we think it might be? Let's have a look. We have got abstraction being B, okay. We've got Bogdan says casting is F. Okay. Yep. Pretty good. We've got Aditya who's saying decomposition is D. Flynn saying B. You could just do 4 letters, one after another. Abstraction is B. Okay. So why don't you try? Because you know you're going to end up producing 4 letters. I should have told you this at the start, to be fair. So what are the 4 letters going to be? So Sergen is saying, he said decomposition is D. Breaking a complex problem down looks good to me. Any more before I flash up the answer? I think you've all had a pretty good stab at this, to be fair. It's pretty easy, isn't it? This is about as nasty as it's going to get. So I'll tell you what, let me give you the answers and then you can see what they were. So hang on, Flynn has come in with DBAF. Bogdan has said that input sanitation is A. Looks good to me. Sergen has also gone for that acronym DBAF. Are we debaffing? It looks like we're in a debaff kind of world. So let's see if we are indeed debaffing, shall we? We are in a debaff world. So that is outstanding. Nice and easy, guys. Really, really good. So DBAF. And in fact, Bogdan, you were correct about input sanitation being A. And I think, was it you, Bogdan, who said about casting being F? Yes, you got that one right. There was 1, 2, 3, 4, 5, 6. What is the one that we didn't get? Repeating elements of a program. What should that have been, do you reckon? Any ideas? E. Repeating elements. Because we've done DBAF. It's easy to remember the, yes, you're right, the input sanitation. And the input sanitation is obviously, that relates to something later on about robust programming, about how you can make your programs harder to hack. Yeah, because it's cleaning up data, isn't it? Sanitation, and we talk about, and the Americans talk about sanitation departments, don't they? And things being sanitary. Okay, and it's obviously, it actually comes from the French word, but anyway, let's not do that. That is good. So I think that's outstanding. I think you are good. C is verification. Yes, it is verification. It absolutely is verification. Well done. That's good. So that's outstanding, guys. Well done. You have got that absolutely sorted. All right, let's push on to a few of these. This is, oh, E was iteration. It was, Bogdan. That's what I was looking for. It was iteration. That was exactly what it was. E was iteration. That was the repeating a piece of a program, wasn't it? So that was excellent. It was iteration I was looking for. I got sidetracked. So this is another exciting round of Guess the Question, where I take the answer from a GCSE paper, and you've got to guess the question. I mean, how much fun can you have on a rainy Tuesday night? What is abstraction? Okay, I'll go back. Hang on a second. Abstraction was the oh, what was abstraction? Abstraction was B. Hiding or removing irrelevant details. So the abstraction, Aditya, that was, let's get you up there. This was the tube map. Okay. So the tube map was hiding or removing unnecessary details to reduce its complexity, okay? Oh! Okay, Ditya. Okay. If I, yeah, you're correct. My bad. No, I know. It's almost as though I wasn't paying any attention, wasn't it? So let's do that instead. So indeed, the question was, and obviously this particular exam board loved to mention themselves in the question. Elliot plays football. He wants to create, at least they've given Alicia a rest because she's usually the one who can't do anything. She can't do anything at all. So lots and lots of waffle, and then define what's meant by abstraction. Okay, so that was the question. Right, there's another part to this. This was part one of this question. Part two, you know, that was very kind of you, Bogdan. I was trying to be helpful, but going in the wrong direction. So here we go. Elliot plays football for them. He wants to create a program to store the results of each football match they play and the names of the goal scorers. Elliot wants individual players from the team to be able to submit this information. Give one example of how abstraction could be used when developing this program. What do you think? So you've got the scenario where it's a program for storing the result of each football match. The result of each match and the names of the goal scorers. Those are the two things they want to collect. Elliot wants individual players from the team to be able to submit this information. Give one example of how abstraction could be used when developing this program. Any ideas, my genii? What do we think could be the answer here? What do we think? This was the second part of this question, by the way. I can't remember how many marks it was for it. I think it's 4, but I can't remember. I think it'll tell me on the next one. Any idea? Okay, so Aditya has said details to consider, score of the match. Okay. Any more takers? Any more ideas? I'll give it just a few more seconds. Not a particularly straightforward one. Not a difficult question, but I think that it's quite hard to formulate an answer for it. So details to consider, the score of the match. I'll give it just a few more seconds and see if we get anything else. Otherwise, I will show you what the answers were. The fact you're so slow to answer this means it's a good one to pick because, hello, we've got Sergen. Consider the scorers and who they played. Okay, that's good. So let me show you what the mark scheme, hello, Chris has come back. By only having them submit their names and match results, nothing more. I like it. Bogdan says, abstraction can be used so the numbers and position of the player is not given. I'll get out of the way. That is good. That is very good. So let's have a look and see what the mark scheme looked like. So it was something like this. 1 mark per bullet point. I think this was worth 4. What Sergen said, ignore unnecessary details about other parts of the match. Yes, yellow cards, etc. So suitable example of what can be focused on, e.g. player name, match results, goals scored. So they want you to demonstrate you've understood what they should be focusing on and a suitable example of what to remove, anything that's not results. In other words, yellow cards. So all of your answers were accurate. And I think that falls into the example of a question that's so easy you think it can't possibly be asking me to state the obvious, but of course it is. Don't forget, this qualification is 9 to 1. So while you taking the exam might be going for a grade 5 or a grade 7 or a grade 9, that's not the same for everyone. So there will be marks on offer that seem like that can't be the answer because it's so straightforward, but it is. So well done. You all, I think, did very well on that one. All right, let's try some more of these. What have we got? 5 minutes left. Which of the following is not done by abstraction? I think we're killing abstraction here. I think we're doing it to death. Breaks the problem down to smaller parts, disregards non-essential information, or identifies central detail. Ooh, there's some answers flooding in here. We have got Bogdan, who is saying A. We've got Aditya, who's saying A. We've got Sergen, who's saying A. Well, I think that's pretty good enough for me. We've got Hash Brown, who's also saying A. So should we give it a go and see what it is coming up with? The answer is A. Outstanding. Right, let's go to our next one. What have we got? 5 minutes left. When drawing a dog, as you do, which of the following characteristics is non-essential? Dogs have 4 paws, dogs have fur, dogs have brown fur. I'd have said that if you're a dog, 2 of those are quite important. But, you know, that's not what the question's asking. So Sergen has said C. Aditya has said C. So we're going for the fur here. Okay, Aditya said C and Sergen said C, and let's see what your Bogdan said C. So yeah, I think that you guys have kind of nailed this. I'll go this way. There we go. It's all C. All right. That is outstanding. And Hash Brown came in with a C as well. You can have your own private ding sound. There we go. Don't say I don't treat you. What about this one? Decomposition allows each task to become, not a dog in sight in this question, more manageable, quicker or easier. What do we think? You see? You see, it's because you're worth it. Do you know what? For that, you can even have another one. Right. Oh, hang on. Chris has come in with a C. And we've got Aditya with A and C. And we've got Flynn with a C. We've got, they're flooding in. Hash Brown with an A. Ooh, the field is split. And we've got Sergen with an A. So let's have a look and see what we've got here. And Bogdan with a C. All right, let's put ourselves out of our misery and see what the answer should be. Although if I press the ding button by mistake, that won't tell us. So let's try this again. There we go, it's A. Decomposition allows each task to become more manageable. I think easier. I understand why you did that, but more manageable is a little more accurate, shall we say? Okay, a little more accurate. All right, then we've got a few more of these to do, but I will stop on time. Identify the steps involved in solving a problem. I'll try that again in English. Identifying the steps involved in solving a problem is the definition of... There's only so many ways we can ask you the same thing over and over again. We've got Aditya who says B. We've got Chris who says B. We have got, they're flooding in. We've got Sergen who says B. Hash Brown who says B. We've got Bogdan who says B. We've got Flynn who says B. Thanks for getting involved, guys. You're absolutely spot on. It's a ding. It's ding time. There we go. So let's get on. What's the next one? Computational thinking is focusing on the important details, breaking a task into smaller tasks, understanding a complex problem and developing possible solutions. What do we think, gentlemen? What is the correct answer here? What is computational thinking? I see the answers are coming in. They're flooding in. Takes a moment to come through. Aditya has gone for a C. Sergen has gone for a C. Bogdan has gone for a C. Chris has gone for a C. Should we put ourselves out of our misery and see what the answer is? It is C. I'll get out of the way. So that is very, 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 very good. We're almost there. 2 minutes to go. I think I've got one more question if I'm correct. I do. Breaking a complex down, I mean, you've clearly got this. Breaking a complex problem down into smaller problems and solving each one individually is what? Ooh, Aditya is saying B. I can see they're coming in. We've got Aditya with B. We've got Chris with B. We have got Sergen with B. We've got Hash Brown with B. And we've got Bogdan with B. Well, I mean, you can't all be wrong, can you? It wouldn't stand to reason. The answer is B. Hurrah. Well, at 8:58, we're going to go on to look at what we're doing next week. So, nice, easy start there. The next time, we're going to look at designing, creating, and refining algorithms. So next week, we'll be looking at identifying inputs, processes, and outputs for a problem and looking at structure diagrams and pseudocode and flowcharts. So we might not get through all of that next week. And I'm aware that paper 2 is the one that you guys would like the most help with, and with the pseudocode part of it in particular. But that will be our focus for next week. I will send out the link for it before half an hour before the actual broadcast, because I completely forgot. So So well done for making it, because you only got half an hour. I mean, I know you knew it was today, but I only gave you half an hour's notice. But I will put it on Satchel 1. I will see you same time, same place next week. Thank you so much for coming, and I will see you all in 1 week's time. Bye-bye, guys. Take care.